Okay, let's continue. Okay, let's continue on in our coverage of machine-level programming, the second in, I think, a 6-part series. As I mentioned yesterday, machine-level programming is sort of the core of this course, that it gives you a set of tools and understanding that take you well beyond what your sort of average run-of-the-mill programmer or software developer would know about. And it's very powerful in terms of your better understanding of the system, what goes wrong, why programs crash, what the meaning of those are. And so it's a fairly core part of the material. As you know, the data lab is due tonight. And the next lab out is called the bomb lab, and I believe that's coming out tonight as well. So the bomb lab will rely on your ability to understand machine-level code. So these 2 lectures will actually be enough to get you started on some of the earlier parts of that lab. You'll learn a lot more at recitation on Monday, either in person or if you're viewing the recorded version of that will help you move along on bomb lab. Like all the labs in this course, or at least the first 2, we give you a fair amount of time for them, but don't be fooled into thinking that means you can just slack off or work on other courses and then in the last few moments jump in and finish this lab. The bomb lab, once you get the hang of what you're doing, it's pretty, you can just kind of crank along, but there's a certain learning curve that will take you to even get started on it effectively. So don't put it off. Where was this? So last time we introduced the very basic principles of machine-level programming, the idea of there being special state that you have access to, the registers, which people came after class and asked, are registers part of memory? No. Are they part of the cache? No. They're special, they're different, they don't exist to a C-level program. When you're programming in C, you don't have any visibility into them. And in general, today what we're going to do then is go beyond the sort of very basics and start talking about the control, how you control the flow of execution of instructions at the machine level, and how you use those techniques to implement basic constructs, conditional statements, loops, and switch statements. And then next time we'll talk about procedures, which warrants a whole lecture of its own. So the x86 and several machines of its generation have these curious little 1-bit flags that are called condition codes. And they're the basis of how conditional operations work. So to a machine-level programmer then, we talked last time that you have visibility of the set of registers and the memory. But you also have more things, and this is only a partial list. Actually, there's more and more stuff that you can add to this picture. But we talked about in the 64-bit x86 64, there's now 16 registers, 8 of which have names that are historic based on old x86 stuff, and 8 of which were introduced, and so they simply name those R8 through R15. And of these registers, for the most part, the only one that's really special is RSP. It's a stack pointer. It tells you where, and we'll learn a lot more about stacks starting next time. But it's sort of where the state is that manages the execution of procedures. And so you can't just use that or set it in arbitrary ways, but the other ones you more or less can, with qualifications to that statement. There's another register that they call the RIP, which has nothing to do with death. It means, the IP means instruction pointer. In IA32 it was called EIP, and now it's called RIP, just like the register used to be EAX, and now it's RIX. So all it contains is the address of the currently executing instruction. And you can take the register that they call the RIP with quality ways, but the other ones you more or less can with qualifications to that statement. There's another register that they call the RIP, which has nothing to do with death. It means, the IP means instruction pointer. In IA32 it was called EIP, and now it's called RIP, just like the register used to be EAX, and now it's RIX. So all it contains is the address of the currently executing instruction. And you can, it's not a register that you access in a normal way, but you actually, there are tricks that you can find out what the value of that is. So that just tells you where in the program, what part of the program is currently being executed. And then there's these things that are called condition codes, and we're only showing 4. There's actually more like 8 of them, but not relevant to our general discussion, that are all 1-bit flags, and they get set not directly, but as a side effect of other operations that take place. And they're the basis for which conditional operation gets decided. So let's go through what those mean. And they're given names, but these names are actually useful to memorize what they mean. So CF means the carry flag. And that's, if you think of adding 2 numbers, think of them as 2 unsigned numbers. And you do the binary arithmetic, and sometimes an extra 1 pops out of the left-hand side, right? That's the carry bit. The numbers you added sort of were too big to be contained in the 32 or 64-bit or even 16 or 8-bit result. And so an extra bit was generated. That's called the carry bit. The 0 flag is what it sounds like. It's set if the value you just computed is 0. These are set typically by arithmetic instructions, by the way. The sign flag is set if the value just computed has a 1 in the most significant bit, meaning it's a negative value. And the O flag, overflow flag, is a 2's complement version of overflow. So in particular, if you remember from data lab, how do you know if addition of 2 values is overflowed? It's if the signs of the operands are the same, but the sign of the result is different than that. So either you added 2 positive numbers and got a negative result, that was positive overflow, or you added 2 negative numbers and got a negative result, that's negative overflow. You can't overflow if the 2 arguments are of opposite signs, right? So those 4 flags result, that was positive overflow, or you added 2 negative numbers and got a negative result, that's negative overflow. You can't overflow and got a negative, sign of the result is different than that. So either you added 2 positive numbers and got a negative result, that was positive overflow, or you added 2 negative numbers and got a negative result, that's negative overflow. You can't overflow if the 2 arguments are of opposite signs, right? So those 4 flags get set as this sort of normal activity by many of the instructions, not by our friend the LEA instruction, which I mentioned is kind of a quirky instruction that GCC really likes a lot, and you'll see it in a lot of places. But in general, and most of the time, those flags get completely ignored, because who cares, right? But they do show up at various points when you're doing conditional operations. So there's some special instructions whose only effect is to set condition codes. And the one that you'll see is especially is called compare, CMP. And by the way, the Q at the end of these is all just a reflection of they're operating on 64-bit words. Quad word, as I said. So the comparison is sort of like a subtraction instruction, except that you don't do anything with the result. A normal subtraction instruction is like x minus equals y. It will read 2 numbers, but then it will store the result wherever x is stored. But compare just takes these 2 values, does the subtraction, and doesn't do anything with the result, but it will set these 4 condition flags. And just a few things to keep in mind that are often will be sources of confusion is, remember that the arguments in the way we write them in machine code is the opposite of what you'd expect. By the way, somebody asked me last time, there's sort of two dialects of assembly code used on x86 machines. There's the one that's used by Intel and Microsoft, and we don't use it. And then there's the one that's sort of used by Linux systems, and that's the one we use. And they're different, and one of the quirks of them is they write their arguments in different order. So it will drive you crazy trying to read. If you're familiar with one, it's like if you've ever tried to drive a car on the wrong side of the road. You often will crash or do bad things. So that's just an aside. That what I find, by the way, when I'm looking at code and I see a compare instruction, I actually write as a comment, compare the two, but I flip the order so that I'm sure that I sort of keep in my mind what the comparison was of. And so these flags get set according to the rules of subtraction. And so it turns out that the carry flag and the overflow flag, you have to sort of flip your sense of what happened because it's a subtraction rather than an addition, but it's the same general idea. So that sort of shows you one particular one. And another instruction that you'll see whose only purpose in the world is to set condition flags, condition of in the way we write them in machine code is the opposite of what you'd expect. By the way, somebody asked me last time, there's sort of two dialects of assembly code used on x86 machines. There's the one that's used by Intel and Microsoft, and we don't use it. And then there's the one that's sort of used by Linux systems, and that's the one we use. And they're different, and one of the quirks of them is they write their arguments in different order. So it will drive you crazy trying to read. If you're familiar with one, it's like if you've ever tried to drive a car on the wrong side of the road. You often will crash or do bad things. So that's just an aside. That what I find, by the way, when I'm looking at code and I see a compare instruction, I actually write as a comment, compare the two, but I flip the order so that I'm sure that I sort of keep in my mind what the comparison was of. And so these flags get set according to the rules of subtraction. And so it turns out that the carry flag and the overflow flag, you have to sort of flip your sense of what happened because it's a subtraction rather than an addition, but it's the same general idea. So that sort of shows you one particular one. And another instruction that you'll see whose only purpose in the world is to set condition flags, condition codes, is the test instruction. And this is typically used, the compare, as you'd think, it's when you have two values and you want to compare them to each other. And the test is if you really just have one value and you want to see what it's like. Is it 0? Is it negative? Those are the main things you care about. In fact, that's the only thing you can determine. But just because I guess they had sort of a possibility of having two arguments to this, so they decided, well, let's go ahead and do it. How do you have two arguments to a test instruction? Well, let's AND the two results and then test that value. So what you'll typically see is a test where both arguments are the same. So test Q %RAX, comma %RAX, so that you're just ANDing a register to itself, and one property of the AND operation is it's what they call idempotent. ANDing two things, the same things together, gives you that same thing. So we can see these, and now, so I told you that's how the condition codes get set. Now how do you actually read them? How do you make use of them? Well, there's two. In principle, you can actually extract and get the condition code values directly out of this special status register, but that's very unusual to do that. What's more common is you either try to read it and set a 1-bit flag based on the result in some other register, or you try and do a conditional branch. So the first example where you try to read it in a way that you can make use of it is done with the set instruction. And you'll see there's a whole range of set instructions, but their only difference is really just what the condition they're setting based on. So what a set instruction does is it sets a single byte of a single register to either 1 or 0. And the basis for whether it sets it to 1 or to 0 is based on what the condition codes are. In essence, what happened to your most recent instruction beforehand? Was it an arithmetic instruction, or a set instruction, or a test instruction, or a compare instruction? And as you can see, they're all based on some logical combination of these condition codes that correspond to what the names imply. So for example, the set S instruction is true if the sign flag is true, meaning that the most recent result was negative. And there's other ones, less than, or equal to was negative. And there's other ones less than, or equal to a single register. First, on the result, so we can see these, and now so I told you that's how the condition codes get set. Now how do you actually read them? How do you make use of them? Well, there's two. In principle, you can actually extract and get the condition code values directly out of this special status register, but that's very unusual to do that. What's more common is you either try to read it and set a 1-bit flag based on the result in some other register, or you try and do a conditional branch. So the first example where you try to read it in a way that you can make use of it is done with the set instruction. And you'll see there's a whole range of set instructions, but their only difference is really just what the condition they're setting based on. So what a set instruction does is it sets a single byte of a single register to either 1 or 0. And the basis for whether it sets it to 1 or to 0 is based on what the condition codes are. In essence, what happened to your most recent instruction beforehand? Was it an arithmetic instruction, or a set instruction, or a test instruction, or a compare instruction? And as you can see, they're all based on some logical combination of these condition codes that correspond to what the names imply. So for example, the set S instruction is true if the sign flag is true, meaning that the most recent result was negative. And there's other ones, less than, or equal to, are 2's complement comparisons, and they have to take into consideration, did the most recent result cause an overflow or not, because that will affect the result of the comparison. So that's part of the reason we tortured you with understanding 2's complement arithmetic and how you compare results, and making you understand the bit level behavior so that you can understand what these instructions do. So we're cruel, but we have a reason for our cruelty. So you say 1 byte, how do you deal with 1 byte? Well, here's another thing we didn't tell you yet, and we're going to keep telling you more stuff over and over again. It turns out for every one of these 16 registers, you can directly set the lowest order byte of it to either 0 or 1, and it won't affect it. It turns out it doesn't affect any of the other 7 bytes of that register. So, and they all have quirky names. The L means low in there. So here's an example of putting all this together to do something that's vaguely useful. Suppose I want a function gt that will take 2 numbers and compare them and set the result, return a result value of 1 if x is greater than y, and 0 otherwise. And so here's the assembly code with some tabbing problems. Fix this. This kind of thing bugs me. Hold on. I might not want to try and do this. Whoa, nope. I will fix this later. Anyways, it's not the end of the world. Normally in assembly code, one thing you've noticed is that the instructions are indented by a tab space, and the only thing that's way over in the left margin are labels. So this is just sort of, the assembler is actually quite tolerant of formatting things, but this isn't the way it normally looks. So anyways, the point is there's the one rule that you need to understand about procedures is that the first argument is passed in register RDI and the second in register RSI, and that if I'm going to return a result from a function, I do that by storing it in register RAX before I return. So the first instruction compares these two, and you notice how I flip the order, that it says RSI, which is Y, and RDI, which is X. But when I annotate it, I say X to Y, so that I mentally am thinking in the order that the actual comparison is made rather than the way they're listed. So I always do that when I'm looking at code to help me flip those two around. And then here's our instruction. So that compare instruction set these 4 condition code registers. And now the set G says, now set this single byte register, the lowest byte of RAX to 1 if the result was, the comparison was greater. So according to this rule. And the effect of that was to set just this 1 byte of this 8-byte register to either 0 or 1. Now my problem is that these remaining 7 bytes have whatever happened to be there before, and I want it to be all zeros. So the way it does it is a bit weird. There's an instruction called move with 0 extension byte to long. Yeah, you get to know these better with time. Let me, and what that means is you can actually copy a byte from any place, like the low order byte of some other register, into a new register, and you'll put zeros to the left of it. That's what they mean by 0 extension. That seems logical, but one thing you'll notice is the destination here is EAX, which you'll recall, although it doesn't show it here, that's the lower 32 bits of register RAX. And then you'd say, well, that only got me halfway there, right? How do I make sure the upper 32 bits are set to 0? Well, one of the weird quirks of x86-64 is for any computation where the result is a 32-bit result, it'll add zeros to the remaining 32 bits of the register. And it's different. For example, the byte level operations only affect the bytes. The 2-byte or operations, like what you'd have if the data type were short, only affect those 2 bytes. But the 4-byte instructions set the upper bytes to 0. And that was somebody at AMD, and I don't know who it is, decided this was a good idea. And it might be a good idea, but it's really confusing. But that's something you'll have to just sort of remember in the back of your mind when you see things like this. So the effect of this instruction is to take this 1-byte result, which is the low order byte of register RAX, copy it to the same place as it already is, but then set the remaining 7 bytes to 0, which is what we want. So you'll see this pattern quite often. We want. So now that's sort of, sometimes I want to do this. I just want to get a 1-bit flag as a result of the comparison. But more generally, I want to do something with that information and not just set 1 bit. So the simplest version is, what about a conditional, an if and possibly an else? Well, that's done by, there's actually two ways to do it. So we'll go through the sort of general purpose traditional way, and then we'll show the more specialized newer way, and we'll compare those. So the traditional way is to use what's known as a jump instruction. And a jump instruction, normally instructions execute in a particular order, just like when you're writing a program and you write a series of statements, they execute one after the next. A jump instruction is a way you can go from wherever you are to someplace else and either skip over some instructions or jump back to some other previous position or wherever. And there's two kinds of jumps. Ones that are unconditional, well, there's several kinds, but an unconditional jump means when I say jump, you jump. But there's others, conditional jumps, that will actually only do that jumping if the condition codes are set appropriately. And you'll see that the names of these jump instructions are the same as the set instructions with the same conditions. So there's a variety of different reasons that the program may be given to either jump or not jump. So I'm going to use this one example to show you several different versions of it. And like everything you'll see here, these particular programs aren't that useful, but they illustrate ideas. So imagine I wanted to compute the difference of two values and then take their absolute value. So there's various ways you could imagine doing it, but the way I'm going to do it is decide to either subtract y from x or x from y, depending on the relative values of those two. And of course, the astute observer will notice that this has problems if you have a t-min somewhere, if the result, because there's no absolute value, but we're not going to worry about that. So in other words, I just want to say if x is greater than y, then I want to subtract y from x. And if x is less than or equal to y, I want to subtract x from y. And here's the code for it, where the blue and the red are color coding the different parts of it. So here you see the compare instruction. And again, I've written them out in the reverse order to help me keep track of what the comparison is. And it says, I'm going to compare x and y, and if x is less than or equal to y, I want to jump to a location specified by this label L4. And so in general, in assembly code, if you give a name and then a colon, what's to the left of that is called a label. And it's just a tag that's only visible in the assembly code. It's not actually in the object code, that will later be used to compute an address for determining, that will encode where this jump will actually land. When you're looking at assembly code, one of the features it provides is a little bit easier way to understand it than to to look at addresses. And so it just tells you to be looking at that the jump would occur to this position. If you give, I want the compare instruction, and again, I've written them out in the reverse order to help me keep track of what the comparison is. And it says, I'm going to compare x and y, and if x is less than or equal to y, I want to jump to a location specified by this label L4. And so in general, in assembly code, if you give a name and then a colon, what's to the left of that is called a label. And it's just a tag that's only visible in the assembly code. It's not actually in the object code, that will later be used to compute an address for determining, that will encode where this jump will actually land. When you're looking at assembly code, one of the features it provides is a little bit easier way to understand it than to look at addresses. And so it just tells you to be looking at that the jump would occur to this position. And what you'll see here is in these two branches, the blue code versus the red, what you're doing is in one case subtracting. This case, so in the first case, you'll make the jump if x is less than or equal to y. You'll subtract y from x, and you'll do a return. And you remember that I don't have to do anything special to return a value back from a function. All I have to do is stick it in register IAX, and the calling function will know that's where to find the return value. So here it does a ret of it, assembly code instructions. So we can sort of take this question.
For the previous slide, did you have to reverse the test? Or is there a way you can do it?
Yeah, I think there's a homework or a practice problem of exactly that sort. So in general, you could do it in either way, and why the compiler picks one versus the other is, I think it's a completely arbitrary decision. But consistently, I found GCC does it this way. Okay, so let's sort of talk, imagine you're writing a compiler. How would you take this special case I just showed and generalize it into a rule for compiling if-then else expressions? And I'm going to use the version of, in C, the question mark colon version, where you kind of encapsulate that whole conditional as a single expression rather than the statement. But you can understand that these rules would be the same in either case. So imagine in general, you had a C code where there's a test controlling whether to return the result of one expression or another. And this is what my absdiff code would look like if I wrote it in that form. And so in general, what we can say is, what we'll do is we'll take the test and invert it and say if that test is not true, then we will, so if n test is true, then we will jump to some part of the code where we've compiled the code for the else expression. And if that test fails here, so that the original test condition holds, then we'll stick in whatever code it takes to compute the then expression, and then we'll merge back together. In the case you saw where it's just a single little function, we can just call a ret here and get out of the thing. But if this is one line of code and then there's a whole bunch of lines after that, typically you want to merge back together again and continue from there. And so that's what this shows. I'll finish by going to whatever comes afterwards. So this is a way I like to, although we're not writing compilers in this course, I think it helps to think in terms of general rules of how a compiler would translate C code into assembly code, so that when you see that assembly code, you'll recognize these patterns and know what they mean. Question?
Yeah. So after it goes to the else clause, does it fall through to the done? Or
Yes. Yes. So just as we saw, yes, in general, like here, it would fall through to the done. Good question. Okay, so that's one version of conditional, and that's the most general way and the way it used to always be done. But there's another approach that you'll see fairly common in code. It's sort of an optimization called conditional move. And it's a bit non-intuitive from a software developer's perspective of why you'd ever want to do this. The basic idea is I'm going to compute both the then and the else, the values they'd produce, and only after that I choose which one I use. So it seems wasteful, but it actually turns out to be more efficient if they're fairly simple computations. And the reason of that is, and we'll see a little bit more when we talk about performance optimization, a modern processor is a little like an oil tanker sailing in the sea, meaning that it plows along in a certain direction, and it really is hard to get it to stop or to turn. So that's, you say, what are you talking about? Think of an instruction sequence as, you know, the ocean of code that you're cruising through. And these things can just fly through a straight sequence of code because they do what they call pipelining, meaning they start bringing in parts of one instruction before they're done with the next, and actually go up to depths of 20 or more instructions deep of how far ahead they're working, sort of fetching forward and future instructions while finishing up the ones that still remain. So that's my ocean liner, my tanker analogy. But all of a sudden you come, and then what happens when they hit a branch, they'll try to guess. It's called branch prediction, and guess where is this branch going to go? Where, you know, will the conditional branch be taken, or is it going to fall through? And they're pretty good at that. They're good at it 98% of the time. So they can even anticipate sort of curves in the road. My analogy is breaking down, and start going in that direction. And as long as they get it right, it's very efficient. But if they get it wrong, it's as if you have to stop the thing, back it up, turn the other way, start again. And that can take 40 instructions, 40 clock cycles, say, to do in bad situations. So, and this is pretty common. If you think of like an absolute value, can you predict whether a value is going to be positive or negative? Not usually. So about half the time, whatever you guess, you're going to guess wrong. So these conditional move instructions, it turns out it's much easier to just plow through, compute both, and then at the last minute, all you have to do is move a value into a register or not. And that doesn't require stopping the whole processor and making this turn. So that's my long explanation for, and if you don't want to understand that, I'll just say, well, just trust me, it's a good idea sometimes. So the general pattern then, if I use the same idea, is I want to compute both results, and I'll call the result, and this isn't eval, this is eval, the else value. I'll compute both of them. I'll do my test, and then this red thing, imagine that's all done with a single instruction that says, I'll copy the value of eval to result, but only if a condition holds. So that's why it's called a conditional move. And we'll see this is the code. By the way, you saw in my original version, sorry to have to jump back, I had to explicitly tell the GCC, don't use conditional moves, because it really wants to very badly. And so you have to force it not to. And I did that here. So here's the actual code then. And again, you'll see the color coding, that it's doing both subtractions. It's actually doing the move and subtract. So it's doing both the branches you saw before, the then and the else branch. It's doing a comparison. And then here's the conditional move instruction. C move, in this case, the L here is not a word size. It's the less than or equal to direction. So in the case that I need the red value, basically, you saw the red value was stored in register RDX. In that case, I will copy it into the result register. So again, it's like this idea of just go ahead and do everything and then pick at the last end. And the point is that this one instruction, it looks just, as far as for this processor execution, it's sort of like a move instruction that it's fairly straightforward to do. Okay, so why doesn't it do that all the time? Well, there's a couple reasons. One is that might be a really, really bad idea to do both computations. If you have to like crack a password in one and find the nth prime number in another, you probably don't want to do both of those. So in general, in that case, and you'll notice GCC will only do this if both branches are fairly straightforward computations that they're trying to do. And there's sometimes when you just plain can't do it. So for example, if you're using a conditional to guard whether a pointer can be dereferenced or not because it's a null pointer, potentially a null pointer, then you really don't want to try that null pointer dereference just as a way to save some time. And similarly, if you could have a side effect, if the result of executing either branch could be to change some other part of the program state, then you don't really want to do that either. And so the conditional move only gets used then in this somewhat special case that you have two computations, relatively easy to do, safe to do, no side effects. But that happens just often enough that this is actually a worthwhile thing. Okay, so that gets us conditionals. And now let's look at loops. That's the sort of next step up in control structures. And C actually has three different kinds of loops. It has a while loop, which you're familiar with, and a for loop, which you're familiar with. And it has a third one, which in my whole life of writing, and I've written a lot of C code in my life, I've used this like about 6 times. So, but it turns out it's the simplest one to implement, so we'll go ahead and do it. So it's called the do while loop. And so the keyword is do, and then there's some stuff you do, that's the body of the do. And then there's a test at the end that tells you whether to keep repeating this loop. So it sort of flips a normal while loop. You have the conditional test at the front, and here you have it at the end. And so it turns out if we think in terms of goto, that's a pretty straightforward thing to replace this with a code that will do a test, and if the test holds, it will jump back and say, OK, re-execute that part of the program I was just in. So it sets up a loop. Data. Main thing to see is this jump if not equal to label L2, and that takes you back to here.
내용들을 활용해서 앞에서 만들었던 음성 비서를 업그레이드 해보도록 하겠습니다. 일단 기능사항으로는 우리가 명령어를 내릴 때 도시 이름이 들어있으면 그 도시의 날짜, 시간, 날씨를 안내해 주도록 변경을 해보겠습니다. 그 다음에는 앞에서 배운 함수 문법을 활용을 해서 코드를 개선을 해보겠습니다. 먼저 기능 추가하는 부분에 대해서 어떻게 작동할지 예시를 보여드리도록 하겠습니다. 서울 날씨,
현재 서울의 날씨는 맑음입니다. 온도는 7.16도입니다.
뉴욕 날씨,
현재 뉴욕의 날씨는 맑음입니다. 온도는 1.94도입니다.
서울 시간과 날짜,
서울 기준 현재 시간은 15시 52분입니다. 서울 기준 오늘은 2022년 2월 10일입니다.
로스앤젤레스 시간,
로스앤젤레스 기준 현재 시간은 22시 53분입니다.
종료.
종료합니다.
원하는 도시의 시간을 알려주는 방법은 여러분들이 구글 검색해도 충분히 찾으실 수 있을 거라고 생각을 하지만 여러분들 시간을 아껴드리기 위해서 제가 찾아놨습니다. PyTZ, 그러니까 파이썬 타임존 패키지를 사용을 하시면 되는데 강의 노트의 예제를 보시면 여러분들 쉽게 이해하실 수 있을 것 같아서 설명은 생략을 하도록 하겠습니다. 세계 날씨도 마찬가지로 여러분들이 도시 이름만 제대로 입력을 해주시면 그 도시의 날씨를 받아보실 수가 있습니다. 오픈 웨더에서 도시 이름을 영어로 어떻게 표시를 하는지 확인을 해야 되겠죠? 제가 여기 링크 걸어놨
Weak-willed fools.
My heart and sword, always for Demacia.
(11시즌) 아이템 강의 이 영상 하나면 템 걱정 끝. 반갑습니다, 진영준입니다. 이번 영상은요 조금 재미는 없을 수 있어도 그리고 주는 티어 흔들지 않는 이상은 쓸만한 영상일 겁니다. 그러면 뭐 신화 가는 모든 신화 아이템이 다 있을 거 아니에요. 그 중에서 니한테 지금 소천사 좋냐? 좀 더 넓게 보면은 스트락도 있을 수 있겠죠. 자, 그리고 파란색 강타는요 내가 뚜벅이가 자주 돼 뚜벅이가 되는 상황이 많아. 이럴 때 파란 강타 갑니다. 상대팀의 이동 속도를 줄여서 뭔가 할 수 있다. 이런 경우에는 이제 파란 강타 가는 거고요. 빨간색 강타는 사실 그냥 그 외 모든 상황입니다. 뭐 맞다이 같은 걸 많이 친다든지 그럴 때 빨간 강타를 가지면 되고요. 빨간색 강타를 언제 쓰느냐면은 이제 내가 어떤 딜 엄청 센 애가 님을 겁나 때려요. 그때 이제 걔한테 강타를 쏘시면은 딜이 20% 감소가 돼서 들어오기 때문에 덜 아픕니다. 그리고 내가 때릴 때 빨간색 강타 언제 때리면은 이제 평타 치면서 빨간 강타 평타랑 같이 나가야 됩니다. 이런 식으로 해주시면 될 것 같습니다. 네, 그리고 그 다음에 신발입니다. 신발은 뭐 간단하죠. 일단 900원짜리 신발 아주 값싼 신발인데 내가 좀 스킬 쿨 같은 게 좀 중요하면은 이제 쿨감신 요거 있죠. 요거 가시면 되고요. 그냥 평범한 상황에서는 신속의 정화 이거는 뭐 딱히 갈 거 없으면 이 아이템 가면 돼요. 근데 이 900원짜리 쿨감신과 대조되게 나는 쿨감보다는 공격 속도가 되게 중요하다. 스킬 쿨타임 같은 게 그렇게 중요하지 않다. 이제 원거리 그 평타 이거 위주다. 이러면 이제 이거 가시면 되고요. 그리고 기동신 같은 경우는 좀 특수한 아이템이죠. 좀 빨리빨리 돌아다녀야 되는 서포터나 아니면은 가끔 정글러들도 가기도 합니다. 아니 로밍을 되게 자주 가는 챔피언들도 가고요. 그리고 닌자의 신발 이거 판금장화네요. 판금장화는 상대팀 평타 많을 때 뭐 미드 루시안 원딜 우리 팀에 AP가 적어. 그래서 상대팀이 마저템 안 가. 이럴 때 마법사의 신발 가는 겁니다. 무조건 AP라고 마법사의 신발 가는 게 아니라 우리 팀의 AP 수가 적고 상대팀이 마저템도 안 가. 이럴 때 가는 거라. 암살자 챔프 좀 상대팀의 방어력이 되게 낮은 챔프들 있죠. 그런 챔프 상대 효율이 되게 좋습니다. 그러니까 한마디로 상대팀이 방템을 안 갈 때 그리고 내가 암살자일 때 이럴 때 가는 아이템이라는 거죠. 하지만 이 아이템 세릴다 원화 이거는 방어 관통력이 30%입니다. 30%를 깎아준다는 건 뭐겠어요. 상대팀 방어력이 높아야지 효율적이라는 거죠. 근데 이 아이템은 효과가